This is a question from J.P. Holman's textbook. Engine oil at 20 degrees is forced over a 20 centimeter square plate at 1.2 meter per second. The plate is heated to a uniform temperature of 60 degrees. Calculate the heat loss by the plate. Now you have a plate which is at TW equal to 120 and you have engine oil coming at 20 degrees Celsius, which is T infinity. And what is U infinity? 1.2 meter per second. Now calculate what is the heat loss by the plate. Now the plate is going to get cooled and the engine oil is going to get heated up. Now we will take the properties of engine oil. First we have to take the Reynolds number. To find the heat transfer, okay, how do you start thinking? To find the heat transfer, what do you use? Heat transfer, Newton's law of cooling, and you will use the Nusselt number, the average value of Nusselt number over the plate. Now, area is known. It's a 20 centimeter square plate, 20 by 20. TW, T infinity is known. What is to be found? The average heat transfer coefficient. So you have to find the average heat transfer coefficient. How do you find the average heat transfer coefficient? By finding the average Nusselt number. And you know the average Nusselt number is twice the local Nusselt number. And how do you find the local Nusselt number? Using the correlations. Now, whether it's laminar or turbulent, the Nusselt number correlation is going to change. So first you have to find the Reynolds number. To find the Reynolds number, it is rho U infinity by mu. You are given engine oil, so you can go and find what is rho and what is mu. Okay, and from the Nusselt number we need H. So let's also find A. So we'll find these three, and page number 33 gives you the property of engine oil. And what temperature do you find this? At the film temperature. The film temperature is the average of 60 and 20. 60 plus 20 by 2, which is 90 by 2. 80 by 2. Oh, sorry, 80 by 2, which is 40 degrees Celsius. So at 40 degrees Celsius, let me write the properties. Rho is 876 kilogram per meter cube. The kinematic viscosity is 241 into 10 power minus 6 meters squared per second, and the thermal conductivity happens to be, or we'll also write the Prandtl number because the correlation for Nusselt number will have Prandtl number. So the Prandtl number is 2870. 2870 is the Prandtl number, and K is 0.1442 watt per meter cube. Prandtl number has no unit. Now first we find the Reynolds number, 876 into 1.2 divided by 241 into 10 power minus 6. This happens to be 'I made a mistake. Reynolds number is U infinity x by mu, right? Here I am finding Reynolds number based on length, so it is U infinity L by mu. That's wrong. L is 20 centimeter or 0.2 meters. So it's 1.2 into 0.2 divided by 241 10 power minus 6. So at the end of the length of the plate, Reynolds number happens to be 995.85. Clearly less than 5 into 10 power 5. It's very small Reynolds number, so the flow is definitely what? Laminar. Okay. Reynolds number is very low, which means the flow is going to be laminar. And the Reynolds number is 995.86. That's right. Now we'll find the Nusselt number based on length. The Nusselt number correlation. You can use the first correlation, 0.332 Reynolds number to the 0.5 Prandtl number to the power of 0.332, but that can be used only for Prandtl number from 0.6 to 50. Here you see extremely high Prandtl number. So if you use that correlation, you're going to get a mistake. In fact, Sensual book ignores that and uses the same correlation. But the textbook by Holman, he clearly mentions that you cannot use that correlation. better to use the other correlation. This is in 1.1.2, same page number 121, but article number 1.1.2 has Prandtl number above hundreds and also for Prandtl number above 50. So this correlation we use 0.3387. Reynolds number to the power of 0.5. Here I will find Nusselt number based on length. Prandtl number to the 0.333 divided by, this is more like the previous correlation, and the denominator we have a correction, 1 plus 0.0468 divided by Prandtl number whole to the power of 0.67, and this is raised to the power of 0.25. Okay. So I'm not sure. I think there's a small typo here. Yeah. 1 plus. Actually, this is raised to the power of. There's a small typo in your data book. You can correct it with a pencil. 1 plus this whole power 0.67. You are given a bracket before 1. Please change it here. And this whole thing is to the power 0.25. Okay. Now we will substitute the values. I have Reynolds number. I also have the Prandtl number. So we just have to substitute 0.3387 into 995.85 to the 0.5 into 2870 to the 0.333 divided by 1 plus 0.0468 by 2870. This raised to the power of 0.67 and 1 plus that whole raised to the power of 0.25. If you do this, you get the Nusselt number based on length. It's a little difficult calculation. First you will do this calculation. 0.0468 by 2870 power of 0.67. Now add a 1 to it, and now you raised it to the power of 0.25. So you get around 1. There's no much difference. 0.3387 into 995.85 to the power of 0.5 into 2870 to the power of 0.333 divided by answer. This comes to 151.46. So you get the Nusselt number accurately like this. Delta Tx. So Nusselt number comes to 151. Suppose you use the wrong correlation, the correlation for Prandtl number between 0.6 and 50, the simple correlation. If you remember, Nusselt number based on mean length will be 0.332 into Reynolds number to the power of 0.5, Prandtl number to the power of 0.333. This correlation if you use, we're going to get approximately the same answer. Right? Let's substitute that 0.332 into 995.85 to the 0.5 into 2870 to the 0.333. This comes to 148.49. So this is exact and that is approximate. For this small difference, they will not cut a lot of marks, but it's better to use the correct correlation. To mention why you are using this correlation, because Prandtl number is very large, it's greater than 50. This correlation is for Prandtl number between 0.7 and 50, and then you are using this correlation, and then you give it, you get the full mark. Senget book uses this kind of thing because it's approximate. You get the approximate value of the answer. Okay, once you get the average Nusselt number, you get the local Nusselt number at LP, you get the average. Twice of that is going to be 151.46 into 2. This will be 302.92. Once you have the average Nusselt number, you can substitute it in H. H bar is nu bar into L by K. I'm going to So this will be 302.12 into 0.2 divided by 0.1442, and you get h bar as 420.14 watt per meter square. And if you substitute h bar here, you're going to get the heat transfer rate. 420.4 into the area is 0.2 square, it's a square plate. TW minus T infinity is 40 degrees. So into 0.2 square into 40. This comes to 672.2 watt. It's going to be the heat transfer. 672.2 watt.